All right, so this is the third lecture for this first unit, concluding, the last part of the cardiovascular system, which are vessels. And so that's what we'll be looking at here, are vessels. We'll be doing vessel anatomy in terms of identifying all the different vessels, but a big subset of the vessels in the body in the lab. So I'm not going to focus on that part. There's a big chunk of the chapter that's just images of vessels and arteries and veins and where they're located in different parts of the body. That's going to be a lab topic for our next lab unit. So for here, talk a little bit about just how vessels are organized and a little bit of structural anatomy, but mostly obviously looking more at the physiology of pressure gradients and how blood flows and how the diameter changes and how that impacts pressure and other types of things. So that's what we'll focus on for this chapter. So the last part of the cardiovascular system are blood vessels. And blood vessels, obviously instrumental to the overall function of the cardiovascular system, is you need a pathway or a tube or something to carry this blood to distribute it throughout the body and to house all this blood so it doesn't spill out in other parts of the body. So obviously the vessel system is essential to that. And so there are different types of blood vessels. As I said, arteries and veins, we've already sort of discussed. Arteries carry blood away from the heart, carrying typically oxygenated blood. Veins return blood back to the heart. And then capillaries are sort of the smallest of the blood vessels, and those are exchange vessels, right, where actually the oxygen is delivered, for instance, and nutrients, but also CO2 and waste products are removed. So anyway, so that's what we'll be looking at here when we talk about these different classifications of blood vessels. Arterials and venules are just smaller branches of arteries and veins, respectively. So we'll be looking at those sort of as we progress. So the largest blood vessels attached to the heart. This carries blood from the right ventricle in terms of the pulmonary circulation, but the aorta, which is the largest component, carries blood from the left ventricle. So if you guys are looking at the heart anatomy, you could see a pulmonary trunk coming from the right ventricle to the lungs to acquire oxygen, but even the larger aorta, which comes up from the left ventricle out to the rest of the systemic circulation. So those are the largest blood vessels. The smaller blood vessels, as I mentioned, are capillaries. They have very small diameter, very thin walls, and this is where we see gas diffusion and chemical exchange and other types of things occurring at this location of capillaries. So if we look at actual structure of vessel walls, you can see three layers: a tunica intima, media, and externa. The intima is the innermost layer, has a thin endothelial lining, as you guys recall from ANP1, simple squamous epithelium lines these blood vessels. Also has a small internal elastic membrane at this location. The tunica medica is the middle layer. Oftentimes we see smooth muscle, maybe some loose connective tissue at this location, and then finally the external layer, or the outer layer, anchors the vessels, has collagen and some elastic fibers, and there's also what's called the vessels of the vessels, the small arteries and veins supplying sort of blood to this location. And so you can look at this image and you can see clearly these three different layers that we're talking about. Sort of in blue or purple is the innermost layer, right, and you can see the simple squamous epithelium. The media is where you have smooth muscle, and then finally the externa is more of a connective tissue. And it has nice inflammation listed here, as you can see in that image. That was of an artery. A vein has a very similar setup. Smooth muscle is going to be more significant typically in arteries than in veins. And this image right here, that was also in the previous one, shows a nice cross-section in the lumen of an artery versus a vein. And the thing you can see most of all, right, look at the lumen of the artery right here versus the lumen of the vein, right? Big difference, right? Much smaller, there's higher pressure typically therefore in arteries. You can see, look at the thickness of the smooth muscle that is there. Much less smooth muscle, larger lumen in veins. So there's a big difference, and we'll talk about those things as we get closer. But those are the three layers. So arteries and veins, right? Arteries carry oxygenated blood. Veins carry deoxygenated blood, typically returning back to the lungs. Arteries and veins pretty much run side by side. They're pretty close to one another. As I talked about, arteries have thicker walls and therefore smaller lumen and higher blood pressure, right? You guys have probably experienced this or have seen, you know, if you've ever had blood drawn from a vein, right? When they pull the needle out, you know, it'll drip a little bit, but it certainly isn't, you know, very much pressure. You can put a cotton ball on there, a Band-Aid or whatever, and you're pretty much in good shape. An artery, if you've ever had blood drawn from an artery, you pull the needle out of there and then the blood is shooting out of there pretty good because there's higher pressure, right? Artery has smaller round lumen, as we talked about, and therefore that helps contribute to that higher pressure. Veins, again, larger, flat lumen, not as much contraction of the lining of that vein. Artery lining folds. Typically, veins have valves. Arteries are more elastic, sort of from that standpoint. So we'll see some examples of that. So arteries. Important component of arteries is elasticity, right? This allows the arteries to absorb these pressure waves that come with the heartbeat, right? Think about that big aorta as that very powerful left ventricular contraction pushes the blood into that artery. It really needs to absorb some of that pressure, and we'll talk about how it has the ability to do that. Arteries can also contract and change diameter. That's a big feature, right? Controlled primarily by the sympathetic division of the autonomic nervous system. We see vasoconstriction and vasodilation, right? Constriction, dilation, we talked about that at the end of ANP1 with autonomic tone without dual innervation, right? We said these vessels are regulated only by the sympathetic division. It either constricts more to contract that smooth muscle or it relaxes that smooth muscle to enlarge the lumen, and resulting in vasodilation. So that's a very significant component of the arterial system, that it has this more smooth muscle, it has this ability to constrict and relax as well, right? And so the vasoconstriction and vasodilation obviously are going to affect what's called afterload at the heart. Of course, it's going to impact blood pressure and then ultimately blood flow to certain capillaries. So we'll see how you have the body has the ability to alter, right, where the blood is going if needed to adapt to certain environments, right? Like exercise is a great example, right? You're going to see more blood being shunted towards those working muscles because those are the ones that are requiring all the oxygen and nutrients to work, whereas other less vital organs in terms of exercise, like digestive organs, for instance, aren't going to get as much blood flow. So anyway, and you can regulate it and control that through vasoconstriction and vasodilation. So that's an important concept to understand as well. Arteries from the heart to capillaries, basically they change from what are called elastic arteries initially, right, because they really need to absorb a lot of that pressure that's coming from the heart, to more muscular arteries, and finally to smaller arterioles as they progress, right. Elastic arteries, also referred to as conducting arteries, right, like the large vessels like the aorta, for instance, has many elastic fibers and not as much muscle, right? And that elasticity can help absorb and even out that really strong, powerful contraction that's coming from the ventricle. Okay? Muscular arteries are also referred to as distribution arteries, meaning that they are, sort of where we're distributing things, blood throughout the body. They're more medium-sized. Most arteries are muscular arteries. And we see more smooth muscle, of course, in this location. Arterials, then, as I said, are the smallest one. Very little tunica externa. Very thin media, so it's really more about getting ready to distribute this blood to the capillaries where gas exchange is going to occur. And so artery diameter, obviously, in the smaller muscular arteries and arterioles is going to change, as we talked about, as a relationship to sympathetic division, stimulation, and more constricted arteries, obviously, are going to oppose blood flow, resulting in resistance. We'll talk about resistance and how you can alter resistance based on the diameter of the vessel. Okay? So, probably you've heard of an aneurysm. An aneurysm is a bulge in an arterial wall, right? It's a weak spot, basically, where there's elasticity that's supposed to sort of control and regulate that flow, and you get this bulge that obviously is not going to be a good thing. Ultimately, potentially, that the pressure in that bulge could cause that vessel to rupture. Aneurysms are very dangerous, obviously, up in the brain aneurysms, as it can really cause severe damage to some nervous tissue, obviously. So, an aneurysm is a weak spot, a bulge in that arterial wall. And so here's a nice overview of arteries versus veins, from elastic artery to then a muscular artery to then arterioles, and then finally we'll see capillaries in a minute, and how blood flow moves, right? And so you can see that. If you take it from the heart, they're more elastic arteries. As it moves away from the heart, they're becoming more muscular, right? They distribute, and then finally, as they get down, you have arterioles, which have some smooth muscle cell endothelium, and they're much smaller as they're getting ready to become capillaries, okay? And there you can see the same thing for veins, which we'll talk about in a minute. And there's another image for the arteries and the capillaries. All right, so that's arteries, right? Taking that initial pulse from the left ventricle, initially sort of evening out the flow, ultimately turning from an elastic type of artery more to a muscular artery. Then it goes down to an arterial, and then finally it turns into a capillary, right? A capillary is the smallest vessel with a very thin wall. They get so small there's sort of these microscopic capillary networks that form and ultimately permeate all these tissues that need oxygen and nutrients, right? And so the capillary function is basically where you have materials diffusing between the blood and that target, right? So all the exchange functions occurring within these capillaries. So that's an important thing to understand in terms of how we'll look at it. So capillary structure, right? Very basic, just basically a thin tube, no media or externa. The diameter is about as big as a red blood cell. Remember, we were talking about red blood cells, and they get to these really small capillaries that have to be able to stack and fold so they can actually work their way into these really small spaces. And so the diameter is obviously very small in those locations. Okay? All right, so there are different types of capillaries based on their structure, and that will lead to the different types of functions that they're capable of doing. So continuous capillaries, for instance, as the term indicates, have a complete endothelial lining. Most tissues have these continuous capillaries, and they permit diffusion of waters and lipid-soluble materials that they're going to obviously block blood cells and plasma proteins and things like that. So it's very common in the body to see these continuous capillaries, right? There are specialized continuous capillaries, like in the central nervous system. We talked about the blood-brain barrier, right? How they are very selective and only allow certain things to cross over. So that's sort of a unique type of continuous capillary that's probably more selective in terms of what can cross over that border. Another type of capillary, which we talked about back in ANP1 when we were looking at the endocrine system, it should sound familiar, are fenestrated capillaries. Fenestrations means like pores or openings in that endothelial lining, where we can see exchange of water and larger solutes. So for instance, we talked about that in certain endocrine organs, like in the pituitary gland, that was important, the choroid plexus, kidneys, intestinal tract, these are all locations where you're going to see fenestrated capillaries. And I have some images here that I'll show you in a second. But and finally, the third type of different structural capillary is what's called a sinusoidal capillary. And these have much larger gaps. So places like the liver and the spleen, certain endocrine organs we're going to see have sinusoidal capillaries that have more free exchange, right? Water, larger proteins. So it's another type. And so as I said, here you can see these three different types: continuous, fenestrated, and sinusoidal. And basically, you're just going from more restricted, in the continuous, to a little bit openings of porous, a little bit more, and then finally larger gaps in sinusoidal. So continuous, fenestrated capillaries. So make sure you understand these different types and the differences and some examples of where you find those types of of capillaries. All right? And there's a close-up of each one. Continuous, fenestrated, and then finally sinusoidal. All right, so when you get to these capillaries, as I said, you get to these sort of microscopic location where you have these capillary beds that ultimately link an arterial with the venule, right? Arterial is the smallest portion of the artery system. Venule is the smallest part of the venous system, okay? And so you have this precapillary sphincter at the site that guards entrance basically to each capillary. So you can open or close or restrict blood flow and regulate blood flow to certain areas. Okay, and so here's where you can see that, right? So this is artery over here, vein over here, or arterial and venule, I should say. And then here you can see the capillary in the middle. And so you have this precapillary sphincter that regulates what's going to happen through here. And as the blood passes through, you can see it changes. It goes from, red, obviously, as the oxygen is given off and the CO2 is required. You then now have deoxygenated blood that they're showing in blue. And so that's the significance of those capillaries, you can see nicely in this image. As it passes from an arterial through the capillary, the gas is given off and now becomes deoxygenated blood returning in the venous system. Okay? And here's a nice image of a capillary bed, right? You can see an arterial here, and you can see, look at how fine some of these microscopic components of the capillary bed is set up. All right. So thoroughfare channels that direct these connections between these arterioles and venules, as we saw in that previous picture. Let's see. Don't worry about collaterals on that last slide. Angiogenesis, you may recall that, is the formation of new blood vessels. We talked about the term anti-angiogenesis factor that's released at cartilage, which is why there is no vessel formation in cartilage. But angiogenesis is the formation of new blood vessels, right? And this actually happens. You have this VEGF, or vascular endothelial growth factor, that helps develop blood vessels and the formation of blood vessels. And angiogenesis can occur when you have hypoxia or oxygen-starved tissues. And so oftentimes, like for instance with cardiac muscle, where you need obviously a constant, steady supply of oxygenated blood, if there's a blockage or a slowing or a oxygen starvation going, the body will actually start to produce little collaterals, they're called. And collaterals are alternate routes of blood flow to sort of bypass the one that's really not working that well. Okay, and so angiogenesis can happen in the brain as well if you have blockages. There are certain disorders like Moye disease where you have really small vessels. Angiogenesis might occur, and you get the proliferation of alternate pathways. Typically, those pathways aren't as effective or as large as what is typically there, but at least it does get some blood flow to the tissue. All right, so vasomotion then refers to a contraction relaxation cycle of the capillary sphincters, which again allows for blood to flow sort of in a specific pattern. All right, so after capillaries, then you have veins, the last portion of the system, right? Arteries, capillaries, and veins. And so once the blood passes through the capillary system, it's now in the venous system, and these veins collect blood from the capillaries and return blood back to the heart, of course, where it's going to reacquire the oxygen and the whole system will start over. So these veins are larger, typically, as we saw in the previous images, in diameter than arteries. They have thinner walls, but most importantly, they have a much lower pressure. So that's a big difference in terms of veins. Venules are very small veins that collect that blood from the capillary. They then turn into medium-sized veins. Again, not a whole lot of smooth muscle. They're getting a little bit bigger. They do have some elasticity to them. And then finally, large veins have all three tunica layers and oftentimes have valves. You may have heard of this. They're folds within that tunica intima that essentially act like a valve, like we talked at the heart, like those AV valves. Right? They prevent blood from going in the other direction. Okay? And oftentimes when your muscles contract, they push these valves shut, and that's why it helps with blood flow walking around and moving, especially from your extremities, can get blood pushing back to the heart and preventing it from flowing back the other direction. Okay? And so here you can see that, right? Here's a closed valve, right? And you squeeze and contract the muscle, it pushes the blood, and it doesn't allow it to return back to that lower portion. All right? So those are what valves are. And oftentimes you may have heard of someone trying to start an IV. Maybe this has happened to you, where they stick the needle in and they get it in there and they think they're going to draw blood, but then the tip of the catheter goes up against a valve wall. And that's very common. And you try to pull blood off, there's no blood coming because it's stuck up against a valve. It can happen. Some people have more valves than others, and just makes it more difficult sometimes to try to insert the needle at a different location in front of the valve so the blood can flow more easily. So anyway, that's something you might come across for those of you going into nursing school from a clinical perspective. All right, so what about the distribution of blood? Okay, because the pressure is so much lower and the system is the vessels are a little bit larger, the venous system actually houses higher amount of the blood at any given moment, right? So the heart, arteries, and capillaries contain about, a third of the blood volume, whereas the venous system is, 60 to 65%. And of that 60 to 65%, a third of that is found in the liver and bone marrow. Remember, we said the liver is a highly vascularized organ. We talked a little bit about that last semester. Bone marrow, skin, other locations where you see a lot of blood flow. So this just shows how blood is distributed throughout the body in terms of where typically it's found. And as you can see, the arteries, not as much. The blood is moving through there faster. They're smaller vessels. And so that's where we're seeing those types of that type of blood throughout the different vessels in the body. All right, so important concept of a blood vessel is its ability to stretch, or capacitance, right? It has the ability to stretch, and these capacitance vessels, like veins, for instance, stretch much more than arteries, and so that, again, is going to be a contributing factor to the relationship of blood volume and blood pressure, ultimately. The more stretch, the lower the pressure in terms of in any given vessel. Okay? And so when, say, for instance, you have blood loss of some kind, we have an injury, or you're losing blood, you have this vasomotor center that can respond to that. It stimulates the sympathetic system. You get some systemic venous constriction, and the veins of the liver, for instance, that carry lots of blood, may redistribute and grab some extra blood in that way to try to maintain blood flow at these other components. All right? All right, so on to a new topic. That is pressure and resistance. So we've sort of at this point have a feel for how these different vessels work, from arteries to capillaries to veins, and we've talked about some of the features of arteries and capillaries and veins. And now we want to start adding some physiology. And obviously the big component, as I said at the outset of this lecture, is that pressure is really what's driving the flow of this blood. And we saw arteries have higher pressure, and we talked about those reasons. Lower pressure in the venous system, we talked about those reasons. And so we want to start looking a little bit more and understanding pressure, and then resistance, right? Well, resistance can create pressure and can cause or have an impact on blood flow. Okay, and so total capillary blood flow, right, is the blood moving to the capillaries, equals what's being created in cardiac output. And it's determined by pressure and resistance, right? If you have a known contraction that's pushing the blood, the only thing that's going to slow it down is either the pressure inside that vessel or any other resistance that may be occurring, okay? And so pressure, the heart generates pressure to overcome resistance, for instance, when it contracts and pushes through those valves, right? And we talked about pressures in each of the different chambers of the heart, when they're contracting. That was a big concept. And so the pressure gradient, or change, delta is what that means, change in pressure, is the difference between the pressure at the heart and the pressure in the capillary beds. And so that's what we're seeing, is from when the heart contracts to by the time it works its way all the way down to the pressure, all the way down to the capillaries, there's a big change in pressure. And so we want to look at that. And so flow then is proportional to the pressure difference divided by the resistance. Now you don't have to do an equation or anything like that, but I want you to at least understand that at a really basic level so we can look at these different pressures and how they change. Okay, so measuring pressure, obviously you guys are all familiar with having your blood pressure read. We'll get to play around with that in lab a little bit where we can get our blood pressure read, and that is measuring the pressure in the arteries, right? And I talked a little bit about this during when I mentioned systole and diastole, but it's measuring millimeters of mercury is the pressure reading in the arteries during contraction and relaxation, right? Systolic over diastolic. There's also capillary hydrostatic pressure. You can get pressure in those capillary beds, and then of course venous pressure. So really there are three ways, right? Arterial, capillary, and venous system. Those are the pressure locations that you want to read. And the change in this circulatory pressure is pretty significant, right? It's about 100 millimeters of mercury. So it's fairly significant in terms of the change. And so the circulatory pressure must overcome whatever peripheral resistance it will encounter in that cardiovascular system. And there are many challenges along the way, which we'll talk about in a minute. So what types of things can cause resistance? What type of components will resist blood flow, essentially? And so there's vascular resistance, which is the vessel wall itself, and the size of the vessel wall, and how much pressure is in there, the blood viscosity, right? We've talked about how blood has a certain level of viscosity because there are cells suspended in a fluid matrix. And then you have turbulence that could occur if there's any kind of blockage or some other type of condition. So vascular resistance, again, is due to friction between the blood and the vessel walls, right? And so it depends on the vessel length and also vessel diameter, more importantly. Vessel length is not going to change, right? We're not going to be able to make our veins shorter. So we really can't look at vessel length. But diameter, right, we talked about how diameter can change based on vasoconstriction or vasodilation or the size of the artery, etc., can really impact. And so the resistance can really increase significantly as diameter decreases, right? The smaller the vessel, the pressure is going to go up, okay, and the resistance is going to go up. Okay, so that's one thing. Viscosity is another thing that can impact, as I said. There are molecules and blood cells and plasma proteins and other types of things in our blood, and so that can cause a resistance, right? Whole blood viscosity is about 4 times of that of water, so it's much more resistant because it has all these cellular components suspended in this fluid matrix. So obviously just the viscosity of blood is going to cause some resistance. And then again, turbulence, as I said, is just any sort of swirling action that can disturb very smooth flow of liquid. Best way to sort of explain this is if you ever go like on a hike or like in Botanical Gardens, for instance, one of my favorite places to go, and you go to some of the nature areas where they have water flowing, and then they have water coming from a smaller area to go out feed into a bigger body of water, and they have rocks along the way, right? So the water passing over the rocks, right? Those produce some turbulence, and that's basically what can happen if you have something blocking a vessel, like a plaque or some other sort of buildup that can happen. And so that can occur in heart chambers and great vessels. Atherosclerotic plaques can cause turbulence, which can impact flow. Okay? And so here's just sort of a visual of what we were talking about, right? Friction and basal length, right? Vessel diameter is a really significant one, and turbulence, right? So that's obviously going to have a very significant impact. Okay? And this just again sort of shows the relationship between blood flow and pressure and circulation. So you want to review that table as well as you're going through it. Okay? All right. So moving on, now that we have a basic understanding of that, we can now look at these overall cardiovascular pressures and what we see as this blood moves through our circulatory system. Okay? And so if you look at these images, we can look at these different factors. It's very interesting because it's on the left here, it's showing vessel diameter, right? The size of the vessel in terms of the opening, the lumen in terms of centimeters. And then this is, going from elastic arteries and muscular arteries, capillaries, veins, and then finally returning back. So obviously these are your largest ones, right? You said the aorta and the elastic arteries, right? You can see have the largest vessel diameter, right? And then gradually as they move to muscular arteries and down to arterials, the diameter of the vessel gets smaller and smaller to where they're the smallest, of course, at the capillaries. And then as the blood moves into the venules, then the veins, and then finally the vena cava, look how much larger you can see. All right? The veins are larger than the arteries in terms of diameter. So that's one factor you can look at. Another one is cross-section. This is a really interesting one because even though the aorta is the largest component, right, of the arterial system, it has actually the smallest cross-section. And because there are so many different microscopic sections in capillaries, they actually have the largest cross-sectional area. Right? So it's very interesting. You'd think, maybe just initially thinking about it, that capillaries would have the smallest cross-section because their diameter is so small, but because there's so many permutations and connections that are occurring within all the different tissues, that actually capillaries have the largest cross-sectional area. What about blood pressure? Well, this sort of makes sense because when the heart contracts with the aorta, right, you get the highest amount of blood pressure, right? That's the left ventricle initially contracting. And then as the vessel diameter changes and come across turbulence and all those factors we talked about, look what happens to pressure. It keeps getting lower and lower until it finally returns back to the heart and it will start back over. So basically it starts with a boom and it's a gradual fizzle until it ultimately returns back to, in terms of pressure, until it gets back to the heart where it can start the process over. Okay? Velocity of blood flow, again, it's moving pretty quickly as it leaves the aorta because, again, very high pressure, right? But then as it moves through and the chamber or the vessels get smaller and smaller, the flow is going to be much slower. As the veins get a little bit bigger, right, flow will increase a little bit as it returns back to the heart, but still much slower than that we see of arteries. Okay? So, arterial pressure then again, as I've talked about before, is systolic over diastolic. That's what that 120 over 80 is, right? Systolic, 120, peak arterial pressure during ventricular systole, and then diastolic pressure is minimum pressure in the arteries during diastole. So that's why you have those two numbers. You can also measure pulse pressure and mean arterial pressure as well. As you guys know, normal blood pressure is typically 120 over 80. Hypertension would be abnormally high blood pressure. Hypotension is also abnormally low blood pressure. So I've talked about, when you think about pressure, and especially when you say the word blood pressure, your probably first thought is, oh man, that's got to watch blood pressure. It's a bad thing. But actually, blood pressure is good. You need a certain amount of pressure in your system, obviously, to make the blood flow and to get throughout the body. So hypertension is only bad when it's really high. And so we talked about that with homeostasis and negative feedback back in AMP1, how your body doesn't like extremes, doesn't like things to be too high or too low. And so you can see that with blood pressure as well. Okay? All right, so elastic rebound, as we talked about before, these arterial walls actually have the ability to stretch, right? And so they stretch a little bit, absorbing that initial force of pulse from the heart as it contracts. Okay? And so the pressure then moves through the smaller arteries and into the arterioles. And you can see how they sort of get arterial pressure, and you can see the change in pressure across this chart, which we've already really talked about at that point. All right, so what about after the blood moves through the capillaries? It goes into the venous system and venous pressure, right? Venous pressure is significant, and then it determines the amount of blood that ultimately is going to return to the heart. Okay, and so it's a much lower pressure in the venous system, as we've seen, as compared with the arterial system. But we have, components that can help with this challenge, right? And so muscular compression we talked about already. Compression of the skeletal muscles pushes the blood back towards the heart. We talked about those one-way valves and how important they are. You also have a respiratory pump in the thoracic cavity as you're inhaling and exhaling is changing blood flow, or pressure in that chamber or in that cavity and helping with blood returning back to the heart. Okay? All right, so what about capillary pressures and capillary exchange? Of course, this is vital to homeostasis. That's the whole purpose of the blood. It has to be able to exchange components, right? And so we'll talk more about this when we do respiration, but we at least want to initially have an understanding of how pressure can impact diffusion and filtration and reabsorption across these capillary walls. Okay, so diffusion is just movement of ions or molecules. So for instance, this is how typically oxygen gets into our target tissues from the blood, right? As oxygen moves down to, say, our muscle, for instance, and you have higher concentration of oxygen in the capillary, lower concentration of oxygen in the muscle, right? The oxygen is going to diffuse across that concentration gradient to move the oxygen into the location or the target, okay? So diffusion is one way. Diffusion routes, as I said, water ions, glucose diffuse between these endothelial cells. Some ions can also diffuse through plasma membranes. Lipid soluble materials like oxygen and CO2 diffuse through those plasma membranes as well. Plasma proteins can only diffuse through sinusoidal components, right? Larger components have to go through fenestrated capillaries. So there are different ways that these components can diffuse and get to their target. Filtration is another one. This is really driven more by hydrostatic pressure. We'll talk about filtration, like for instance at the kidneys, right? And how that's how your body produces urine, is through hydrostatic pressure. So we'll look at filtration more specifically when we do the urinary system and look at the kidneys. And then reabsorption is also something that's really important. We'll talk more about that in some in the urinary as well as some in the digestive pathway, where a really important compound of that is to be able to reabsorb fluid. So reabsorption is an important compound. And this just sort of shows how hydrostatic pressure can drive the movement of smaller solutes through those pores or sinusoidal locations. All right, so what about cardiovascular regulation, right? We are constantly adapting to a different environment. Even if you're sitting now listening to this and you pause this and you get up and you walk, you get a drink of water and come back, that's your body and your heart and your cardiovascular system is going to have to adapt to that, okay? And so cardiovascular regulation and adaptation are some topics that we're going to look at here in this next segment. So first thing is tissue perfusion, right? As we know, the blood flows through the tissues. It carries the oxygen and the nutrients toward the tissues and those targets and those organs and pulls away CO2 and waste products, right? And that tissue perfusion is impacted by cardiac output, right? How much blood is being pumped every stroke and minute. The peripheral resistance, of course, how much resistance is impacting it, and then blood pressure. These are all going to impact tissue perfusion at a given target, okay? And so the body has to regulate blood flow to a certain area depending on what's going on, right? It needs to be done at the right time, in the right location. And what's also really important is you can't impact blood pressure to vital organs. So in my example previously, I was talking about exercise, right? Your body has to redistribute more blood flow to, like, say, if you're running, to your quadriceps, right? So those, and your hamstrings, so those leg muscles can work more efficiently as they require more oxygen and fuel. But it still needs to, supply blood to the brain and to the heart. And so we see an adaptation that occurs. And there are different ways that the body does this, okay? And it can do it through what's called autoregulation, right, which is immediate, localized adjustments that help maintain homeostasis. We have neural mechanisms that we talked about, and then also we can talk about and then endocrine changes. So autoregulation is basically just the change in blood flow within a capillary bed to alter blood flow. So for instance, if you have normal blood pressure and normal blood volume or homeostasis, and that homeostasis is disturbed at a specific location, it could be physical stress or a change in oxygen levels or pH. And the problem is, of course, inadequate local pressure and flow. And so you need to alter that, right? Have vasodilation occur. That's going to increase blood flow to the target. Homeostasis can be restored and you're back in business, okay? So that's autoregulation, sort of an autoregulation process primarily through the dilation of blood vessels or vasodilators, right, in that specific location. Central regulation involves more neural mechanisms, right, where we have regulatory control over these, like the vasomotor center, for instance, an endocrine mechanism that can regulate homeostasis, right? So we have, for instance, the cardiovascular center, which is going to stimulate heart rate, and the vasomotor center, they're going to regulate vasoconstriction. These things can all help your body adapt when you sort of have a changing environment and get back to homeostasis in terms of blood flow to a certain area. Okay? So autoregulation, again, is adjusted by these local vasodilators, right? And I talked about the different mechanisms there already that can cause that to happen. There are also local vasoconstrictors that can also alter blood flow to a particular area. As I already mentioned here with the cardiovascular centers, right, they also can either increase or decrease heart rate as needed. The vasomotor center can regulate vasoconstriction and vasodilation by, adrenergic or cholinergic nerves, right? That's going to help, regulate that blood flow we talked about before. There also are baroreceptors and chemoreceptors that actually respond to changes in blood pressure. So blood pressure changes, you have reflexes that are going to correspondingly either cause vasoconstriction or vasodilation to adapt to that change. Chemoreceptor is the same kind of thing, where you see a change in gases or chemical composition that result in a certain type of reflex, right? So, for instance, baroreceptor reflexes. The right atrium can monitor what's going on in the systemic circuit, right? And with stretch receptors, as more blood is flowing back to the heart, is going to be impacted and allow more blood to flow then into the right atrium. Okay. Baroreceptor reflexes, again, when blood pressure goes up, right, you're going to see a decrease in cardiac output and maybe see vasodilation, right, to help lower blood pressure a little bit. If pressure gets too low, right, your body may respond by increasing cardiac output and cause vasoconstriction as well. So these are just adaptive mechanisms that the body has. Again, homeostasis. If you have an increase in blood pressure, right, the baroreceptor is going to be stimulated because the pressure is going up, and so you might decrease heart rate, decrease constriction on blood vessels, so output's going to go down, vasodilation is going to occur, and you get back to normal blood pressure after blood pressure has gone up. Right? That's what happens when you can respond to that. All right, and then this again shows just the opposite, right? Decreased baroreceptor. Pressure starting to get too low, right? Basically the opposite thing will happen and return it back to homeostasis. So just look through those as I talked about in terms of knowing how the body can adapt to those different receptors. Okay? All right, chemoreceptor reflexes, I sort of talked about these already. They monitor changes in chemicals which can impact CSF or respiratory or blood flow to the brain, so a change in pH or oxygen level can then coordinate a change in corresponding cardiovascular or respiratory activities, right? And so again, these images are nice. Homeostasis is normal, let's say oxygen level, for instance, right? And so if you have decreased oxygen level or increased CO2, right? Chemoreceptors, the chemical responders to those types of things, are going to respond. You're going to see respiratory rate go up. You're going to see cardiovascular stimulator, center stimulated vasomotor stimulation, and you're going to see decreased CO2 because you've gotten rid of more of the lungs, more oxygen, and you're going to get back to a normal level. So those are another way the body can adapt to that. All right, so the cardiac stimulation, vasoconstriction are basically what help regulate these processes. Hormones can also impact these components, but they're more sort of long-term from that standpoint. And we'll talk about, for instance, ADH, an antidiuretic hormone, and how it can impact that. Probably more when we look at the kidneys and how that works. Okay. We'll look at angiotensin too as well when we look at the kidneys. EPO is a hormone, as you guys know. We talked a little bit about that already. That's going to respond to low oxygen content and stimulate red blood cells. That can increase blood volume, which could also increase blood pressure. Okay, and so this just sort of shows those effects. We'll talk more about angiotensin and the role of the kidneys more later on in the urinary system. All right, so we can see how this cardiovascular system adapts to changes by either increasing or decreasing heart rate and regulating vasoconstriction, vasodilation. That's the primary method by which the body can alter these pressure systems. And so if you look at this cardiovascular system as a whole, the whole thing has to work together to maintain homeostasis. The heart, the blood, the cardiovascular system with the vessels, everything has to work together. And so a great example of how your body adapts to these changes is what happens when you exercise. So I want you to make sure you take a moment to look through the body's response to exercise. So for instance, in light exercise, you see vasodilation occurring, which is going to increase circulation. You're going to see venous return increasing with those muscle contractions, right, because that helps squeeze the blood and pump it back to the heart. And so as a result, cardiac output goes up with exercise. It's called the Frank-Starling principle, that as venous return goes up, you're going to see arterial stretching, and again, you're going to get more blood flow pumping throughout the body. Okay? And after heavy exercise, we see sympathetic nervous system activated, cardiac output goes way up. Again, as I said before, it restricts blood flow to non-essential organs, like the digestive system is a great example. Your body is not concerned about digestion when sympathetic stimulation is going up, right? It redirects blood flow to the muscles, lungs, heart, blood supply to the brain. It may increase a little bit, but for the most part, it's not going to go down. Blood flow to your brain is always essential, of course, and that's something that's important to understand. So this is a great chart that I want you to, you don't have to memorize this, but generally have a nice understanding of what's happening at rest, during light exercise, and strenuous exercise in terms of blood flow and distribution. So look at, say, for instance, the skeletal muscle. During rest, you have about, 1,200 milliliters per minute of blood flowing through your skeletal muscle. During light exercise and strenuous exercise, look at how much it goes up, right? And that makes sense, right? Your muscles that are working, you need more oxygen, you need more nutrients, so obviously you're going to increase blood flow to those areas by altering vasodilation and allowing more blood to permeate those tissues, okay? Look at the heart, same thing. At rest, going up during light exercise, and even more during strenuous exercise, right? The heart is working so much more, there's more blood flow going, as we mentioned. The brain, as we said, is pretty much staying the same. The skin, it's going up, right? Think about why is blood flow to the skin going up? Well, remember we talked about how it's going to help cool you down, right? You can get vasodilation to those blood vessels that are closer to the skin surface. You can lose some heat that way until that will help cool. But look at the kidneys and the abdomen, for instance, right? These are all pretty much staying the same. And you can look at cardiac output, going down significantly, right? Kidneys, so urinary and digestive, right? Not as concerned, so blood flow is sacrificed there, but everything else is going up. But if you look at total cardiac output, light exercise versus strenuous exercise, look how much more blood flow is pumping. And that makes sense, right? Because heart rate's going up, more blood flow is being pushed around, and so you have more cardiac output occurring. So this is a really nice slide that you want to make sure you have a good understanding of what's happening there. Okay? All right, so what are some of the benefits then of this cardiovascular fitness and health and exercise? A lot of you guys will know all this stuff already, like lowering blood cholesterol levels and impacting the body. But too much of a good thing could also be, intense exercise can cause damage or physiological stress that could be harder to return. This is another nice chart that's really good to sort of have an understanding of, is what's happening in terms of cardiovascular performance in the body in a non-athlete versus a trained athlete, right? Look at probably the biggest example is heart rate, right? Look at the non-athlete heart rate at rest is 83, non-athlete maximum is 192. Look at the trained athlete. Look at rest, how much lower it is compared with the non-athlete. And think about why that would be. Why would somebody who's a trained athlete have such a lower resting heart rate? Well, the reason is that your heart is a muscle, right? It's a pump, and it becomes a more efficient pump. The more you use it, the more efficient it is at pumping, so it doesn't have to work as much to meet the demands of the body, right? In fact, look at this trained athlete. Even though the heart rate is so much lower, look at how much blood is being put out, 5.3 liters per minute, whereas much more work in the non-athlete, 83, and they're actually putting less out. So that tells you that a lot more blood is being pushed around more efficiently by the trained athlete. Blood pressure also, I would say you'd probably see a lower blood pressure here in the trained athlete than you would in the non-trained, but you get the point. So anyway, this is a good chart to sort of compare the differences in stroke volume and heart rate and blood pressure and all those kinds of things in trained versus untrained. Because exercise does have a significant impact. The cardiovascular system's response to hemorrhaging, right? We talked a little bit about this before, but it's really going to try to maintain blood pressure initially, because if your pressure gets too low, blood's not going to get to all the important tissues and you could have some serious issues. But long term, it needs to then restore blood volume, right? And so if you're having, an injury or something where you're losing blood, right, short term, you're going to try to get pressure up, right? Because if you're losing blood, pressure is going to go down. And so you're going to increase cardiac output, get some vasoconstriction going on, constricts arterioles, improve venous return to try to maintain blood pressure, right? Vasoconstriction will continue, right? We've seen a lot of those hormonal effects that we talked about briefly as well starting to happen. And the short term could be, if it's not maintained, you could see a shock occurring. If blood volume is significantly lost and you can't maintain blood pressure, it can be very dangerous, okay? So once you've managed the hemorrhaging, right, so you have some sort of injury and you stop the blood flow finally, now it's more a matter of restoration of blood. And so EPO is going to stimulate red blood cell. Thirst will increase, right, because what is your blood made of? Water and blood cells primarily. So thirst is going to go up, EPO is going to stimulate red blood cells, and hopefully you'll get restoration of blood flow and pressure back to normal. And so this is, again, a chart just sort of showing how this works in terms of normal blood pressure, and if you have extensive bleeding and decrease in blood pressure and volume, how are these things going to be impacted to restore homeostasis. So we can look through that illustration to sort of go over those components. All right, so vascular supply, again, there are separate mechanisms to regulate blood flow to the brain, heart, and lungs. As you might guess, those are very vital organs, and so they need to regulate, right? Blood flow to the brain is top priority. Brain has a high oxygen demand. As we talked about before, the brain does not have the ability to store sugar as well, so it needs a constant supply of sugar, obviously a constant supply of oxygen, and you can regulate blood flow in that regard, okay? And that can help is essential. Stroke, as you guys know, is also referred to as cerebrovascular accident, a blockage or rupture of the cerebral artery, which is supposed to deliver oxygenated blood to that region, stops blood flow. If it hemorrhages, right, then you're really going to get a lot of blood in the brain, which can cause a lot of damage, of course, as well. And so stroke is a very significant and very serious injury that can occur as a result of a blockage of these cerebral arteries. Blood flow to the heart, of course, is very important through those coronary arteries that you guys are currently learning. Oxygen demand is going to go up. The more you're working, right, the more the heart's going to be working to pump blood throughout your body. So it needs oxygen. And so you'll see dilation of those coronary vessels to increase coronary blood flow to meet those demands that are occurring. Epinephrine can dilate coronary vessels, increasing heart rate as well as strengthening contractions. You know that is a sympathetic neurotransmitter that can impact that. And so a heart attack, obviously, just like we saw in stroke, is a blockage of blood flow to the heart, right? And you can see we talked a lot about these things already with chest pain, tissue damage, heart failure, but ultimately could lead to death as well. Blood flow to the lungs is regulated by oxygen levels in the alveoli, right? If you have high oxygen content, vessels dilate. Low oxygen content, vessels are going to constrict more to try to push more oxygen down to those, more blood to those locations. Okay? Last thing we'll wrap up here with, just a few slides, is the impact of aging. Age-related changes really occur in all components, so the blood, the heart, and the blood vessels in the cardiovascular system. The blood, we see a decreased hematocrit, right? We talked about hematocrit, and that is how many red blood cells you have, the count, a percentage count of red blood cells in the blood. And it decreases as we get older. You see a slower amount of cell division and cell production. You can have blockages by some sort of blood clot or thrombus. You get pooling in the blood in the legs due to valve deterioration, right? Those things can all have an impact. At the heart, we've seen a lot of things. Your maximum cardiac output is going to go down. Your conducting cells may not be efficient, in terms of driving heart rate. Big one is reduced elasticity, so the cardiac skeleton is not going to be as elastic, which is going to make it harder to impact or make it harder for the blood to increase cardiac output. Atherosclerosis, of course, we've talked about that. Scar tissue typically replaces any damaged muscle cells. If you had any sort of areas of infarct that might occur, that can also be impacted. Arteries become less elastic. We talked about an aneurysm. Calcium deposits on vessel walls, plaques can rupture, causing strokes or infarctions from those atherosclerotic plaques. So those are all things that we can see that can happen. These disorders may affect, all cells and systems. Structural or functional result from disease or trauma as well. All right, so that wraps up the lecture. Should be good to go on these first three. We'll do a lecture exam coming up on these, this first unit, which is all the three components of the cardiovascular system. So let me know if you have questions, and that is it.